Hello and welcome to the lecture on deep learning in this course. And what I want to talk about today is the first in a series of two lectures I'm going to be giving on convolutional neural networks. And if we just start from the beginning on this. So convolutional neural networks. We've talked a lot about deep learning, and I want to go into a little bit of detail of how we actually do it. So we've got questions we might be asking, such as what is machine vision? Well, I tried to cover that a little bit so far in the course. What is convolution? And I talked about that a little bit as well. Then what are we talking about with machine learning? And what is a neural network? Then what's the difference between a neural network and deep learning? And why do people tend to be interested in deep learning? And why do some people not like it, I guess you could ask. And why do we need to know about deep learning at all? And what two case studies we'll cover. So as you know, machine vision is where we have a camera, which is an industrial camera, and sometimes we can have a 3D camera, such as a RGBD, maybe RealSense, for example, or Connect, and but a lot of the time we'll be doing 2D images, such as you get with your average typical camera that you got built into your mobile phone nowadays. We could also look at thermal imaging, where we're looking at the near infrared or longer infrared frequencies, or we can look at multispectral, where we can detect different frequencies. In fact, any camera you buy will have a response generally of spectral response, and you need to make sure that's suitable for the application you've got, depending on the light sources you're using. You want to make sure you've got good sensitivity in the area where you're using for the illumination for your problem. And then this is some of the stuff we've been doing in the lab. I just included some of this stuff here. This was a non-contact breathing measurement system that we developed a few years ago, and it worked quite well. But the prototype worked well, as you can see there in the lab. But there's a difference between having the prototype working well and actually having something you can use in the ward and start selling. So it needs to get over the valley of death, really, to get towards commercialization, which is always difficult. It requires a lot of work and money to do that. But we got a nice journal paper out of that one, actually. That was quite good. And then we did a project. We touched on. I've been dealing with medical work quite a lot, but also we're doing agri-tech, quite a good deal. And this was a project where we used deep learning to look at pig faces, and used it to identify pigs. And you can see the different colours here. What these colour map indicates is how much the neural network, or CNN, used of particular areas of the image in order to identify the pig. And you can see that it was a forehead in this case, and the snout here because it's redder indicates more usage of the network. But the idea was to identify pigs rather than having to put tags on them, which is expensive and of course hurts the animal to some extent. It's completely non-invasive. We just take images, and we have them having a drink at one part of near the front of the cage, and we just take images every time they come for a drink, so we have loads of images. But that worked very well. We identified the pigs quite accurately. And then with the next project, we went on to detect their emotional pig, to see whether the pig was distressed or not. And we found we can do that also with deep learning. That's in collaboration with Scottish Agricultural College. It's been on Netflix, actually, that work. It's got quite a high profile. This down here is Wenhow, and you can see this is the system we developed for the London Underground, where you can see that it's a false colour image, where the surface normal orientation is related to the colour. So if the normals from this side of the face are red and this side blue, and you can see the whole morphology of the face there is represented in this. This was using a photometric stereo technique, which I would talk quite a lot about. Now the great beauty of this is you can easily differentiate between Wenhow's real face and just a photograph. This thing you can see is all the same kind of colour, same photo there, and the same Wenhow there. So this immediately gives you more security, because all these systems that exist at the moment, 2D ones, can be fooled by just holding a photograph of somebody else in front of your face. So this is the next generation of face recognition systems for airports, really, and the London Underground. They're not using it that much on the Underground at the moment, because they're still finding that they're happy with the gates at the moment, but this will sooner or later be employed, and it will really reduce congestion on the London Underground. So a couple of examples. So a typical machine vision pipeline, then what's going on here is, first of all, we're acquiring the image, of course. Then we've got to do some pre-processing. Okay, we might do some segmentation, filtering, or we might even do some edge detection. Background, foreground segmentation. So you know what you want to do is segment foreground and against the background to make it clear that's the thing you're interested in that you want to analyze. Then we might do some feature extraction, where we get information like distances, coefficients, color, textures, spatial frequencies, and so on out of there. So we're getting a feature vector with each parameter in the feature vector giving us some measure of the feature characteristic. After we've done that, we might want to do some classification. This would be where the neural network would come in. So we want to differentiate between, in this case, between bananas and hammers. And, you know, there are different approaches you can use for this. Support vector machine would indicate certain vectors or planes or lines separating two different types. Or you could use deep learning with a convolutional neural network, which is a powerful technique. And I'll go into some detail. So that's what we're talking about, classification. Humans can easily see the difference between a banana and a hammer, but you have to make the computer do it, which is not that necessarily that straightforward when you've got all sorts of different images. So what are neural networks? I mean, I mentioned them before a little bit in one of the lectures, and I will mention them again because it's not the most obvious thing. It requires a little bit of explanation. What it is basically is a pattern recognition technique that is data-driven. That's what it is in a nutshell. And it's inspired by the biological neural networks in the brain. And maybe the guy who dreamt it up in the early days was Frank Rosenblatt in 1958. And he called his first crude neural network something called the perceptron. I'll talk about it in just a second about Frank. But each neuron inside, and these are the neurons, these nodes of the neurons, has a transfer function that relates its input to its output. So the value that goes in is related to the output. It's just a means of relating it. If you had a linear one, it would just be a straight line. But we want a nonlinear one because we want to model nonlinearity, because it's very common in industry to have nonlinear situations. The model here in the neural network is stored in the weights, multipliers of each of the links. So these links, right, linking together the neurons in the neural network, have a weight associated with them. Now these weights are just multipliers, so the value that comes out here is multiplied by this weight and goes into there. And the model is stored in these weights. So when you start trying to train the neural network, all these weights are assigned to random values. And then the training indicates changing them, modifying them to certain values which give you the recognition of the pattern that you want. You say that the network converges. They all cut these values of these weights tend to converge on a solution which will, when you put certain values in, will give you the value out that you want. Talking about Frank, I did a sketch of Frank. This is Frank Rosenblatt, and he dreamt this idea of the perceptron up. And unfortunately, though, he was responsible for an article that appeared in the New York Times in 1958, was it? Talking about how he believed perceptrons were going to be able to walk, talk, see, write, reproduce, and be conscious of their existence. And I think a lot of people thought that was a little bit fantastic, you know, when they heard that. So I think, to be honest, he oversold it a little bit. And what happened there was that when people realized what you could actually do with these things, they were a little bit disillusioned. And this led to the fact that neural networks were more or less forgotten about from 1958 through to the 1980s, which was a bit of a shame because Frank actually died in a boating accident in Chesapeake Bay in 1971, I think it was. So he never got to see these things take off as they did in the 80s. He was actually quite a forward thinker, interested in all sorts of things in addition to his psychology background at Cornell. He was interested in contact with extraterrestrial intelligence, which I thought was pretty progressive. And he actually built an observatory behind his house. It's the kind of thing I'd like to do, to be honest. And I don't suppose he ever made contact with any extraterrestrials, but he had sort of all sorts of different interests in science and technology, this guy. The Mark I perceptron that he invented can be seen in the Smithsonian in Washington, D.C. It's considered to be quite important. But you know, so what happened with another reason perhaps why neural networks were kind of forgotten about is because people thought they couldn't model non-linearity. They thought that was a problem. But when they employed more of these layers of these neurons, 2 and more, and they actually had these nonlinear transfer functions, they discovered you could. You could model all sorts of nonlinearity, just about any function, in fact. And that's why they got that. That's one reason why they had this sort of rejuvenation in the 1980s. Another reason why they really took off was because people worked out a good way to train them, a good way to modify these weights depending on what the data is indicating. So the way this works is that you feed some data in, the data propagates through the network, and you get some outputs. You're doing your multiplications and so on. The outputs are then compared to the expected outputs. The outputs you get from your network are compared to the ones you got written down in your data. And the difference is the error. And then what you do, the way this works, is you back propagate through the network, changing these weights iteratively so as to minimize the error. And that's why this is known as a feed-forward backpropagation neural network. That sounds a bit complicated, but that's actually the simplest type of neural network, feed-forward backpropagation. This was invented a while ago. I mean, there was the big characters who were responsible for lots of developments in neural networks were Geoffrey Hinton, who's in the UK, who did a lot, especially with deep learning. Jan LeCun, who developed a system for detecting handwriting on checks, which is still being used by banks, I believe, in now. He invented it some time ago, 99 or something. So he's really the guy who got deep learning first working at all. And there's one or two other guys, Andrew Ng and so on, other guys you might hear of. But these are called the godfathers of deep learning, these guys, actually, because they did a lot, and they're still doing a lot of research nowadays. But when they invented this backpropagation technique, then that's when it really took off, because then you could train the networks. I should mention, I suppose, that the neural network is obviously implemented on a computer, such as your IBM PC, so it doesn't actually physically have these connections, not the way it's been implemented by most people, but they're simulated in the computer. It runs a simulation of this, and that's the way it works. So data going forward, data propagation, error backpropagation. So what's the difference between deep learning and regular neural networks? Well, deep learning involves more neurons than previous networks as a general. Utilization of explosion of available computer power for training. In other words, just lucky, I guess, that these gamers come along with their GPUs, which actually are very great for number crunching, which is the kind of thing you need to do with a convolutional neural network and deep learning. You can do automatic feature recognition. We'll talk about that in a minute. And we have something, the most standard technique we use is convolutional neural networks. So I'll go into a little bit of detail there. A convolution, what is convolution? Now I mentioned, I did go through, didn't I, before, what convolution is, but I probably might be worth covering it again just here. Convolution is a common image processing technique that changes the intensities of a pixel to reflect the intensity of the surrounding pixels. That's about it, really. And a good use of convolution is to create image filters. Using convolution, you can get popular images like image effects, like blur, sharpen, and edge detection. This is an image that's been used since 1973 to illustrate some of these image processing techniques. And this is a soften technique, or like a blurring technique. So this is the original image, then you apply your blur filter, softening filter, you end up with this. To achieve the effect, such as that, convolution is performed using a grid-like mathematical structure, which we call a kernel. So there we have, for example, a 3x3 kernel. The height and width of the kernel don't have to be the same, but they've got to be odd. The reason for that is you need to have a central pixel, or central value, if you like. Numbers inside the kernel are what impact the overall effect of the convolution. So depending on what these values are, it determines what effect this convolution is going to have on the image. The kernel, or more specifically, the values held within the kernel, is what determines how to transform the pixels, the original image, into the pixels of the processed image. Convolutions are pixel per pixel operations. The same arithmetic is repeated for every pixel in the image. Bigger images therefore require more convolution arithmetic than the same operation on a smaller image. So that's why you don't necessarily want very high resolution images if you don't need them. You don't want to go above what you need because you'll have more time required for this kind of processing. And of course, the bigger the kernel is that you're using, the more computation you'd require as well.
So this is the way the convolution works. The numbers in the kernel represent the amount by which to multiply the number underneath it. The number underneath it represents the intensity of the pixel of which a kernel is hovering. The process multiplies each number in the kernel by the pixel intensity value directly underneath it, resulting in as many products as there are numbers in the kernel. The figure below shows how that's working. The figure here shows how it's working. So the center element of the kernel is placed over the source pixel. There, center element. The source pixel is then replaced by the weighted sum of itself and the nearby pixel. So you multiply each of these values in the kernel by whatever these intensities are in the image, and then you sum it up. In this case, you get an answer of -8. And then you replace that central pixel value with this new value. That's how it works. If you were doing this softening thing that we showed in the previous image, well, a couple of images ago, this kind of softening operation, this can be performed by something called a mean filter. So what that would be is that if you were doing the mean filter, you'd have ones in each of these values in the kernel, and then you'd do all this multiplications, and then whatever value, you sum it all up, and then you'd divide by the number of elements in the kernel. It would give you kind of a, it gets rid, it's useful, the mean filter, because apart from softening, it can also get rid of noise, like speckle noise in the image. It was used on the Apollo flights to get rid of some of the speckle when Neil Armstrong was stepping down from the lunar module. You get rid of noise, you get speckle, but it does, you do lose some resolution, so that's a downside, I guess, that approach. Another way of getting rid of noise is just to get rid of any objects in the image which are, below a certain area. Examples of kernels use image processing, so edge detection. The pattern that you have in the kernel affects what kind of edges you could detect. As it says here, the final step of the process sums all the products together. In the case of the mean filter, divided by the number of numbers in the kernel, and this value becomes a new intensity that was directly in the center of the kernel. So there we go. These are different kernels for different types of edge detection. So, what this is that, if you've got an edge of an object in the field of view, all you really want to know is where that edge is. So you do this edge filter to put a line to sort of accentuate the edges to make the measurement process easier. It's data reduction again as well, really. Rather than having all the huge amount of data in the image, you just have the edges in this case. And depending on the kind of edges you're trying to detect, you have different values in the kernel. And of course, when you apply that kernel, you have to keep scanning across the whole image doing that. And then when you've done that across the whole image, you've got it filtered to produce those edge filters. So this is an example in LabVIEW, whereby we've got the original image, we've applied this filter, and then we've got this edge filter here. Sort of demonstration someone rigged up. But how does convolution help us with automatic feature identification? Because this is one thing that these CNNs can do, is automatically work out, without you having to tell it, what the filter is, what the feature is you're looking for in an image. Well, what you do is you apply a range of different types of filters. So supposing the first filter is a 7x7 kernel, and we're looking for something like a curve detector. Now the curve detector, so this is the kernel that might represent a curve if you're trying to detect this kind of curve, and you get higher numerical values along the area that is in the shape of the curve. And there you see these 30s representing this line here, basically, as you can see. Now, when we have this filter at the top left corner of the input volume, it's computing multiplications between the filter and the pixel values of that region. Now let's take an example of an image you want to classify, and let's put the filter at the top left corner as it says here. So this is the image we've got of this mouse, and we're trying to work out what's going on at the top left corner of this mouse image here, which is where we're applying the filter. So we multiply the values in the filter with the original pixel values of the image then, don't we? This is convolution. If in the input image there is a shape that generally resembles a curve that the filter is representing, then all of the multiplications summed together will result in a large value. So this is the image data from the mouse, back of the mouse, and this is our filter. So we're doing this multiplication summation as per convolution. We say visualization of receptive field, that's what the mouse looks like in that area, in other words. This is what that receptive field looks like in terms of pixel values, and this is our kernel for the filter. So this is what the convolution operation does. We get the 6,600, a very large number, as a result of this convolving here.
Now let's try and move this filter to a different point on the mouse. So let's go for the mouse's head there, top of the mouse's head. So this is the values we've got for the image in this region, as you can see here. And we've still got our same filter, and we're doing the convolution, but if you convolve those two, you end up with 0. So the value is much lower because there wasn't anything in the image section that was corresponded to the curve detector filter. So this is a very simple example of how this works, just to get the concept across. In reality, you would use much more complicated combinations of filters. So as it says here, the output of the convolutional layer is an activation map. So this is what we call it. We do that convolution over the image and we get something coming out called an activation map or feature map. In the simple case of a one filter convolution and the curve detector, the activation map will show areas in which there's most likely to be curves in the picture. So we're really looking for these features which are curves in this case. Just one kind of filter. Outward and to the right in this case, we have other filters, lines and curves in other directions and straight edges. The more filters, the greater depth of the activation map, and the more information we have about the input. We use different filters to work out what's going on in different regions of the image. And in reality, we convolve these filters around the input image and activate when specific features it's looking for is in the input image. Now, as I say, that was a simplistic one. In real CNN applications are more complicated, so you get all sorts of a whole range of filters looking for different types of things in the image to give you these are visualizations of the kind of filters that might typically be used in deep learning. Now, so how big is the first hidden layer of a CNN, you might ask? Well, suppose you had an image 32 by 32 and use a 5 by 5 filter. The first hidden layer would be a 28 by 28 array, because there are 784 different locations that a 5 by 5 filter can fit onto a 32 by 32 input image. These 784 numbers are mapped to a 28 by 28 array. So this is the input neurons, and we've got this hidden layer coming up here. So the activation maps form the hidden layers. And so the convolutional layer is the core building block of a CNN. The layer's parameters consist of a set of learnable filters or kernels. Each filter map shows the detection of some specific type of feature, some spatial position in the input. And then what we do is we stack these activation maps for all the filters along the depth dimension, and it forms the full output volume of the convolutional layer. So people talk about sort of three-dimensional convolutional layers, okay? So but be careful when you hear that, because they're not talking about three-dimensional data as in we're talking about a lot of the time, three-dimensional machine vision. They're simply talking about stacking these layers from the convolution, the feature maps, one after another to build up this sequence of data to give you the results of the activation maps for all the different filters, okay? You can imagine that a lot of data is building up as you do that. That's one problem you've got to deal with, a large data buildup. But there are some techniques to try to limit that problem. One technique you could use is incorporate something called a value layer, where you remove negative values. That just helps with the training. But another important thing is pooling layers. So this is what you do in this part of the convolutional neural networks. You get these feature maps building up, but you're getting a vast amount of data building up, so you have to reduce the amount of data. So pooling is just where you reduce the amount of data in the layer. So it just reduces the data in order to make the thing manageable, really, to stop it going out of control in terms of data. And it does that by combining the outputs of neuron clusters at one layer into a single neuron on the next. You can look this up. If you look this up, there's a lot of information on the internet about this, and I can't give a completely in-depth introduction to it all in just a couple of lectures. I guess it's such a big subject, but I just want to get the basic concepts across about how it works and what you can do with it, really. So you do this stuff called ReLU and pooling in order to reduce the data that's in there. And then what you have towards the end of the section of the convolutional neural network is something called a fully connected layers. And here you connect every neuron in one layer to every neuron in another layer. This is like, as I showed you earlier, in terms of a traditional multi-layer neural network. The fully connected layers classify the images. So that you're starting off with all this stuff here with convolution to basically determine what kind of features are in the image. And then you're getting more and more analysis there. And then as that data is being generated, you're using your fully connected layers at the end here to actually classify the images, you know, dog, cat, car, human, whatever it is you've got in your image, different types of feature classification. So convolutional neural networks summary. Convolutional neural networks automatically identify characteristics of a data set that can be used as reliable indicators, i.e. features. So automatically identify features. That's quite a big deal, actually, because what we used to have to do years ago, we used to have to, what they call handcraft features. If you had to work out somehow what kind of features were in the images corresponding to what we wanted to identify. You know, what does the feature of a dog look like? What's the feature of a car look like? The trouble with that is that it's a lot of work trying to work out what the best kind of features are. It's also a bit prescriptive. In other words, I'm kind of dictating what I think the features are we should be looking for. I don't really want to do that. What I really want to do is to extract the features from the data. Suppose I'm looking for weeds in grass, okay? I might try and dream up what features of a dockweed look like, okay? But they may not be, it may just be my impression of a dockweed. It may not be much like what they actually look like when you start capturing data images in the field. So what we want to do is get the system to automatically generate the features from the data, and that's what a convolutional neural network can do. And as a consequence of doing that, the response of it, the performance will be better than it would be if I tried to manually say what these features look like. As it says here, historically the convolution approach was for research to put vast efforts into exhaustive sets of features for image classification. Since the advent of deep learning, CNNs, the conventional approach has been exceeded in accuracy for almost every data type. So that's another big advantage of CNNs. The accuracy with which they work in terms of pattern recognition is far better than any other approach, really. Deep learning, that is better than other approaches. It's like, for example, when there's a thing called ImageNet, where they had these competitions to try to have, say, 1 million images or however many it was, and you had to do feature recognition, face recognition, say, in this data. And they were getting all sorts of error, and they had a prize every year for the person who could do it the least error and the most accuracy. And Jan LeCun did it, analysis. Was it the first, was it ImageNet? No, sorry, this is ImageNet. I think this was Geoffrey Hinton who worked on this, what I'm talking about here. But maybe it was in 2012 this really took off, because somebody decided to use deep learning on this in 2012. And they demonstrated, I'm trying to remember, something like a reduction from 26% error to just 15%. So it was a dramatic increase in accuracy that was demonstrated, and that sort of fired everybody's imaginations, and that really led to the takeoff of deep learning and CNNs. And so that's what really got it going, and we find that the accuracy is really good, even in situations where the data that we're using has got all sorts of noise or errors associated with it. You know, I could be looking for weeds in grass, and the light could be changing all over the place. There could be shadows. There could be different types of weeds. I could be viewing them from different angles. But the thing about deep learning is it's remarkably robust, even in the presence of those kind of variations. Those kind of variations would have thrown off the accuracy years ago for other techniques. But with deep learning, we're finding they're remarkably resistant to those problems. One slight disadvantage that has been, apart from the computation that is required for the training of the CNN, is that you used to require a lot of data to train the CNN. Once you trained it, you can just consult it quickly and easily, but you need to train it. Now, they used to require a lot of data, but there are some techniques that we've been coming out recently that we've been looking into in our lab a lot. For example, transfer learning and data augmentation. I'll go into a bit more detail about those later on, but they're remarkable in terms of you can get good network performance even with very limited sets of training data. Another thing you have to do, of course, is get the network to generalize. So that's where you split your data typically into the training and the test data. You use the training data to, not surprisingly, train the network, and then use the test data, which the network's never seen, to see how well it can actually detect things it's looking for in practice. This is very important because you don't want it to be heavily, to overtrain on the training data and then find it won't detect anything else outside of the training data. So it's very important that the network generalizes. So that's something that you'll come across if you ever get into this in more detail. Anyway, that's an introduction, the very, very brief introduction to CNNs and deep learning. I will give another lecture. I'll go into a bit more detail and I'll make a few notes here and there. But I hope you found that useful as a sort of introduction to the subject. And it's a very powerful subject. And every time I go to a conference, someone's using it in a new way. And the two, the research PhDs that I'm supervising are both using sort of in-depth versions of CNNs, different types. So it's something that you need to be aware of and something that's really very powerful. So thanks for watching. I'll see you guys next time.